The topic of a synchronous machine continues, and in this example it is creating a similar or a realistic scenario that there is a factory or a plant, and let's consider this plant to be like this. We have a factory unit or a plant, and we are creating a single line diagram. That means that, for example, from the utility, from the SEC, there is a transmission line coming, and this is this distribution, and inside the factory, and the factory has one motor and two motors, large huge motors, or we can say motor bays or units where multiple induction motors are installed. So they are connected, and it is calling it as L1 and L2, and L1 and L2. L1 is an induction motor, and it has given its power. It is consuming 100 kilowatt, and its power factor is 0.78 lagging. Low 2 is also an induction motor which is consuming 200 kilowatts, and its power factor is 0.8 lagging. Now there is also another motor, load 3, connected, which is a synchronous motor, and it is consuming a real power of 150 kilowatts. Now what's the power factor for this? This is unknown, basically unknown. So this is the scenario for our simple factory unit, and what we need to understand is here we have induction motor, here we have induction motor, and here we have synchronous motor L3. So we must to understand this phenomena, the whole question lies on the fact of power triangle. What is power triangle? Power triangle is a relationship between real power, that is represented in watts, reactive power, which is represented in VAR, and then there is apparent power, that is represented in V of A. And the fact also lies here regarding this thing is that for the value of VAR, we can there is the theta, and cos of theta is actually this angle, that is the power factor for the machine. And we should also know that it is the angle between the voltage and the current. So if the current is lagging, then the value of theta will be positive, and theta will be positive, then Q would be positive. And if the current is leading, then theta, the value of theta will become negative, and the value of Q will also become negative. That means the load is supplying reactive power. So the whole question relies around this basic formula, and you can also see that if we know P and if we know theta, we can calculate this value by tan of theta is equals to Q over P, or we can say the reactive power is P tan of theta. Some people have curly brown hair till painted black. So tan theta is, so if a synchronous motor is adjusted to operate at 0.85 power factor lagging, what is the transmission line current in the system? So first of all, we have to calculate the transmission line current in the system, and the transmission line current can be calculated if we know the total power of the system. So let's start solving this. So for load 1, let's look at load 1. We know P equals to 100 kilowatt, and the reactive power P1 we can say is actually equals to Q1 is equals to P1 tan theta, that is actually equals to P1 tan cos inverse, because we have the power factor also 0.85 here, so we can put 0.85 here, and this will become Q1 equals to 80.2 kVAR. So this is the amount of kVAR. As it is positive, this means that it is consuming P and it is also consuming Q, the first induction motor. For the second load, in the similar fashion, second load we have P1 equals to 200 kilowatt, and we also know that it has a power factor of 0.8 lagging. So we can get this as same as above. The value of Q2 will become 150 kVAR. That's it. And for the real power of the load and reactive power of load 3. Now this is important. Now our synchronous motor is also acting with this much power factor. So for the load 3, we know the real power that our load is consuming is P3 is actually equals to 150 kilowatt, and this in this scenario our motor is acting with a 0.85 lagging. And I would like to highlight this fact that the synchronous motor has the magical power that we can change this from lagging to leading. Power factor can be changed by the field current control. So in the similar manner that we calculated in above, we will have 93 kVAR for the load 3. So we have calculated. So what is the total? So the total load for the factory, PT equals to P1 plus P2 plus P3, and that will equals to 450 kilowatts. Total load, real load. This is known as real power or the average power or the real power. And total reactive power would be Qt equals to Q1 plus Q2 plus Q3, and we will add all the Qs, and this will become 3 to 3.3 kVAR. This will be the total reactive power. And the equivalent system power factor is, because what is the transmission line current in the system? So we are in the search of transmission line, but we have PT and QT. We can find the total power factor for our system, and power factor would be, we know that tan of theta equals to Q over P. From here we can get the value of theta, and then when we take cos of this theta, we will get the power of this, and this will become 0.812 lagging. So the power factor of the overall machine is overall factory unit is 0.812 lagging. Or we can say that this is, and to calculate the transmission line current, what is the current that is being supplied? We know that the total power, we have the real power. It can be calculated by different ways, but I'm using the real power. You can calculate by apparent power or the reactive power, but the formula is under root 3 VL, because line to line voltage, IL cos of theta, because we are able to calculate this theta. So, and for calculating this theta, we have calculated first P and Q, and then we have calculated cos theta. So the value of IL will become, what is P total? Let's look at the question. No, P total we have calculated here. This is 450 kilowatt. What is VL? 4 operates as 480 volts, and the value of VL is 480. And cos of theta we know, so the value of IL would be 667 amperes. So this is actually for the part A. And now let's look at part B, in which it states that the power factor of the synchronous motor is now changed. How we change this? By changing IF, we are able to change the value of internally generated voltage EA, and also we are able to change the power angle for the motor, and from positive, and in this way we are able to not from positive to negative, but we are able to change this angle by changing the amplitude, and also we make our generator generate reactive power instead of absorbing reactive power. So to achieve this, now for the similar conditions as for part B, now synchronous motor power factor is 0.85 leading. So we must know that for the real power, P1, P2 and P3 will not be affected by this change, and so our PT will remain same. What the thing will change, the only thing that will change will be Q3, that is the power being generated or absorbed. So in this scenario, Q3 will be generated by L3, and we can calculate this. Q3 is equals to P3 tan theta, and previously as we calculated theta we know, and from here we can calculate the value, and the value will become minus 93 kVAR. We can see that now the Q3 is in negative. This means it is being generated by the motor, synchronous motor. So Q total will now change, that is equals to Q1 plus Q2 plus Q3. Q1 will remain same because this will keep on absorbing Q1, its power factor is same. Q2 is absorbing, it will remain same, but only for the synchronous motor we have changed the excitation and it is now providing Q3. So for this scenario, now the QT will become 137.2 kVAR, and of course as this will change as we have calculated previously. Now if we calculate for the overall system, then theta is equals to QT over PT. We will calculate theta, and for cos of theta we will find out that it is 0.957 lagging. So we can see that we have changed the power factor. It was 0.812 lagging, and now we have changed it to 0.957 lagging by the field excitation control. And the last part that shows the main advantage of all this activity, one thing has remained. We have to calculate, when we have calculated this, we have to calculate the line current for our new power factor. So we calculated in a similar way. We will calculate it. Now the power factor has changed and the value of IL will be, if we calculate, 566 amperes. Same way we have calculated, only this cos theta has changed. And in the last scenario, we are required to calculate the losses are given by this equation, and what it wants to calculate is For part A, calculate the losses. For part B, calculate the losses and see how much is the difference between the losses. So for part A, we know that IL was 667 amperes. So line losses, PLL is for line losses. And the formula for this is 3IL square and RL. So have they given us RL? So if they have not even given us RL, we can see that we put this value and this value would become 1344700 RL, which can be any value. We can assume 1 also for the same case. But we are for the part B, when the line current has been decreased to 566 amperes, so PLL will now be 3IL square into RL. This becomes 961.070 RL. And if we make the comparison between them, how much percentage reduction? So 28% reduction has been seen in the transmission line losses by adjusting the excitation of the synchronous motor. So how this 28% comes? This if I assume this value to be old and this value to be new, so it is actually percentage change formula is old minus new divided by old. So we get, because RL for both the scenarios is same, so this is transmission line the losses. So there is 28% reduction for the SEC, and this is 28% reduction in the line losses due to just adjusting the excitation of your synchronous motor. And in this way, the billing for the factory will be less and the line losses for SEC will be the less, and this will act as power factor improvement device in the grid. I hope it helps. Thank you.